The device you're listening through right now, whether it's a phone on the nightstand, or a laptop somewhere in the room, or a small speaker on a shelf, is, by some honest measures, one of the most complicated objects that has ever existed. Billions of tiny components, doing tiny jobs at extremely high speeds, coordinated in ways that almost nobody who uses them has ever been told about. That's what we're going to walk through tonight, slowly in ordinary words, with nothing being asked of you on the other side. Get comfortable first, though, wherever you are. The day is done. The lights, if they're still on, can stay on or go off, whichever you prefer. Pull the blanket up to where you like it. Let your shoulders come down from wherever they've drifted to over the course of the day. Soften your jaw. Let the small tension behind your eyes ease. You won't need to remember any of this. That's the arrangement we have on these recordings. If you fall asleep 3 sentences from now, the story keeps going without you, and it'll still be here in the morning if you want to come back to it. If you wake up at some odd hour and have lost the thread, that's also fine. Nothing in the rest of your life depends on you holding on to a single thing you're about to hear. What we're going to do is take that small complicated object you're using right now and walk layer by layer through what's actually inside it. By the end of the story, you will know, in some real sense, how computers work. Not the way an engineer knows, the way a person who has been told the truth knows. Even if you fall asleep most of the way through, even if you don't remember any names or dates, something will have settled, somewhere in the back of your mind, where understanding lives, and you will know more than you did when you began. That's the promise of the title. We're going to actually do this thing. One small thing before we begin, and then I'll stop talking about anything except the story. If you'd like a voice like this in the dark on other nights, other long, quiet things to drift to tap subscribe now, before you forget. And if you feel like it, leave a comment with where you're listening from. People do, and it turns out there's something quietly nice about scrolling through later and seeing a few hundred other people in a few hundred different rooms, all settling in for the same long night. No pressure on either one. Just if you want to. Then we can settle in for real, and I won't ask you for anything else tonight. The story begins in 1936, in the basement of an old building at the Massachusetts Institute of Technology, with a graduate student named Claude Shannon, who has been staring at a wall of electrical switches and beginning to suspect that the mathematics he studied in college might have something to say about them. Chapter 1: The Young Man in the Basement. Claude Shannon was 20 years old when he arrived at MIT in the fall of 1936. He had grown up in Gaylord, Michigan, a small town in the northern part of the state, where his father had been a probate judge and his mother had been the principal of the local high school. He had gone to college at the University of Michigan, where he had earned 2 degrees at the same time. One was in mathematics. One was in electrical engineering. The combination was unusual. Most mathematicians of the time did not study engineering. Most engineers did not study mathematics beyond what they needed for their work. Shannon, who was quiet and unusually focused, and had what people who knew him often described as a kind of cheerful detachment from ordinary concerns, did both. At MIT, his first job was as an assistant in a basement laboratory, where the engineering department kept what was, at the time, one of the most complicated calculating machines in the world. The machine was called the differential analyzer, and it had been built by a MIT professor named Vannevar Bush. The differential analyzer was a mechanical computer. It used a system of rotating shafts and wheels and gears, driven by an electric motor, to solve certain kinds of mathematical equations. To configure the machine for a particular problem, you had to physically reconnect its mechanical parts using a complicated arrangement of belts and clutches. To control the configuration, you used a panel of electrical relays, which were small switches that opened and closed in response to electrical signals, and which routed the control signals to the appropriate parts of the machine. Shannon's job was to maintain and operate the relay panel. When a researcher wanted to use the differential analyzer to solve a particular equation, Shannon would set up the relays in the right configuration so that the machine's mechanical parts would be connected in the right way. The work involved a great deal of staring at wiring diagrams, a great deal of moving small components around, and a great deal of testing whether the configuration he had built actually did what it was supposed to do. After some months of this, Shannon began to notice something. The relays, when arranged in particular patterns, seemed to behave according to rules that reminded him of something he had studied in his mathematics courses. Specifically, they reminded him of a kind of mathematics called Boolean algebra, which had been developed in the 1850s by an Irish mathematician named George Boole. Boolean algebra was a small and elegant system that dealt with statements that could be either true or false, and with the operations you could perform on such statements. The operations were called AND, or AND not. The AND of two statements was true only if both statements were true. The OR of two statements was true if either of them was true. The not of a statement was the opposite of the statement. Boole had shown that these three operations were enough to express, in a precise mathematical form, any kind of logical reasoning that human beings did when they thought about whether one thing implied another. What Shannon noticed in the basement was that electrical relays could implement exactly the same operations. A switch was either open or closed. Open could represent false. Closed could represent true. If you put two switches one after the other in a line so that the current had to pass through both of them to reach a light bulb at the end, then the bulb would only turn on when both switches were closed. That is, in effect, an AND. Both switches on, bulb on. Either switch off, bulb off. If you put the two switches side by side instead, with each one offering a separate path the current could take, then closing either one would turn the bulb on. That is, in effect, an OR. And a switch that could be wired to do the opposite of what it was told, opening when energized rather than closing, was, in effect, a NOT. This observation, which Shannon spent the summer of 1937 turning into a master's thesis, had a particular consequence. If electrical switches could implement Boolean logic, then any logical operation that could be expressed in Boolean algebra could be performed by a sufficiently complicated arrangement of switches. And Boole had shown 80 years earlier that all of the logical reasoning that mattered could be expressed in Boolean algebra. Therefore, by combining enough switches in the right way, you could build a machine that did logical reasoning. You could, in a sense, build a thinking machine out of wire and metal. The thesis was titled A Symbolic Analysis of Relay and Switching Circuits. Shannon completed it in 1937. It was about 70 pages long. It has since been called, by various computer scientists who have written about the history of their field, the most important master's thesis of the 20th century. What Shannon had shown was that you could build computers out of switches, not analog computers like the differential analyzer, which used continuous mechanical motions. Digital computers, which used only on and off states. And critically, you could design such computers using mathematics in the same way that you could design a bridge using mathematics rather than by trial and error. The mathematics in question, the Boolean algebra that Shannon had connected to switches, would, over the following decades, become the foundation of how every computer in the world worked. The basic operations Shannon had identified, the AND and the OR and the NOT, would still be the basic operations performed by every computer chip, billions of times per second, 80 years later. The chips themselves would change. The switches would change from clumsy mechanical relays to delicate transistors etched on silicon. But the logical structure of what they did would be the same logical structure that Shannon had laid out in his 70-page thesis in 1937. Shannon's work also implied something else, which became clearer over the following years. If the basic unit of computation was a switch that could be either on or off, then the basic unit of information was a single yes or no answer. A single bit. The word bit had not yet been coined when Shannon wrote his master's thesis. It would be coined a few years later by Shannon himself in a paper he wrote in 1948 about a related topic that he called information theory. The word was a contraction of the phrase binary digit. A bit was the smallest possible unit of information. It could take exactly two values. It could be a 1 or a 0. It could be a yes or a no. It could be a true or a false. It could be a switch closed or a switch open. Everything inside a computer, in the end, is made of bits. The numbers the computer works with are sequences of bits, arranged according to a system called binary. The letters of text are sequences of bits, according to a code that assigns a particular number to each letter. The images on the screen are sequences of bits, where each bit describes whether a small dot is lit or dark, or what color it should be. The sounds from the speakers are sequences of bits, describing the rapid up and down motion of a speaker cone. Everything that a computer can store or transmit or operate on is, at the bottom, a long sequence of ones and zeros. This is the deepest fact about computers, and the one that's hardest to wrap one's head around when you first encounter it. The photograph on your screen, the song playing through your headphones, the words of an email you're reading, the address of a website you're visiting. All of these things, when the computer is actually working with them, are just very long sequences of bits. They differ from each other only in how they are interpreted. The same sequence of bits could, in print, be interpreted as a photograph one moment and as a piece of music the next. The bits don't know what they are. The computer doesn't know what they are either. The interpretation is imposed on the bits by the programs that use them. What turns a sequence of bits into something meaningful, a number, a letter, an image, a sound, is the rules that the program applies. The rules are themselves stored as sequences of bits in another part of the computer. The whole machine, top to bottom, is bits operating on bits according to rules made of bits. It is in some way a strange thing. It is also, when you sit with it, a very simple thing. Everything inside the computer is one of two values. Everything the computer does is the application of Boolean logic to those values. The rest is detail. How that detail actually gets organized, and how a collection of switches can be persuaded to behave like a thinking machine, is the work of the rest of tonight's story. The 80-year-old mathematics that Shannon found in his basement was the foundation. The question we'll come back to, again and again, is how people built upward from that foundation, one careful layer at a time, until they had a machine you could carry in your pocket that could do anything. Chapter 2: The Shoemaker's Son. The mathematics that Claude Shannon found in the basement at MIT was 80 years old by the time he found it. It had been worked out, in a town in Ireland, by a man named George Booley, who had died long before there was any reason to suspect that his mathematics would have anything to do with machines. Booley was born in 1815 in Lincoln, a small cathedral city in the east of England. His father was a shoemaker who, by most accounts, was more interested in mathematics and astronomy than he was in shoes. The Boole household was poor. George was the eldest of 4 children. He left formal schooling at the age of 16, not because he had finished it, but because his family needed him to work, and there was no money to send him to university. What Booley did instead, over the next several years, was teach himself. He taught himself Latin from a grammar book his father had borrowed. He taught himself Greek. He taught himself French and German. He taught himself, and this was the unusual one, advanced mathematics, working through textbooks alone in his room in the evenings, after he had finished his day's work as a teacher at a local school. He read, by his own later account, every mathematical paper he could find in the small public libraries of the towns he lived in. He saved his teaching salary until he could afford to subscribe to mathematical journals from London. He worked slowly and patiently, by himself, in a way that very few people would have the discipline for. By his late 20s, Booley had become, by self-study alone, one of the more skilled mathematicians in England. He published papers in mathematical journals. He corresponded with established mathematicians who were surprised to learn that he had no formal training. He developed a reputation, in the small world of British mathematics, as a person worth knowing. In 1849, at the age of 34, he was offered a professorship at Queen's College in Cork, a new university that had been founded a few years earlier in the south of Ireland and that was willing to hire a self-taught mathematician without a formal degree. Because they could not afford anyone better established. Boole accepted. He moved to Ireland. He spent the rest of his life there. It was in Cork, between 1849 and his death in 1864, that Boole did the work that mattered most. In 1854, he published a book called An Investigation of the Laws of Thought, which laid out the system of mathematics that has since been called Boolean algebra. The book was, in his own view, an attempt to do something that philosophers had been trying to do for over 2,000 years, which was to put logical reasoning onto a precise mathematical foundation. Boole did not think of his work as having anything to do with machines. The idea of an electrical computer would not exist for almost 100 years. He thought of his work as a contribution to philosophy. The laws of thought, in his view, were the rules by which the human mind moved from one idea to another. He was trying to express those rules in mathematical form. The mathematics he produced was simple but powerful. He proposed that any statement that could be either true or false could be represented as a variable, like the letter X in ordinary algebra. Two such statements could be combined using three basic operations, which he denoted using the same symbols that ordinary algebra used for multiplication and addition and subtraction, although they meant something different. With these three operations, Boole showed you could express any compound logical statement you cared to make, and the compound statements could be manipulated using the same kind of algebraic rules that you might use to manipulate ordinary equations. You could solve them. You could simplify them. You could rearrange them. You could check whether one statement was equivalent to another by performing a series of small algebraic transformations until you arrived at a known answer. The system, when Boole published it, was received politely but without enthusiasm. The professional mathematicians who read it found it interesting but not obviously useful. The philosophers who read it found it too mathematical to engage with their concerns. The book sold modestly. Boole continued to teach in Cork, raised a family, and worked on other mathematical problems. His death in 1864 came in a particular way that is sometimes told as a story. He had walked the 2 miles from his house to his lecture hall in the middle of a winter rainstorm, and had arrived soaking wet, and had then lectured in his wet clothes for the full hour, because changing would have meant delaying the class. He caught what was, at the time, called a chill, which developed into pneumonia. He died a few weeks later. He was 49 years old. What happened to Boolean algebra after Boole's death was that it sat on shelves. For about 70 years, almost no one used it. It was taught occasionally as a curiosity in advanced mathematics courses. It appeared in textbooks of mathematical logic. It was studied by a small number of philosophers, but it had no practical application that anyone could point to. It was a mathematics in search of a purpose. The purpose, when it finally arrived, came from the basement of an engineering laboratory in Massachusetts in the form of a graduate student looking at a wall of electrical relays. Shannon, when he made the connection, was applying Boole's work in a way that Boole could not have imagined. The pure mathematics that had been written down in Cork by a self-taught Irish professor in the 1850s turned out to be exactly the mathematics that electrical engineering would need in the 1930s to begin building machines that thought. What Shannon's discovery enabled in practical terms was the design of what came to be called logic gate. A logic gate is a tiny electrical circuit made of a small number of switches that performs one of Boole's 3 operations. There are AND gates, which produce a 1 only when both of their 2 inputs are 1s. There are OR gates, which produce a 1 when either of their 2 inputs is a 1. There are NOT gates, which produce the opposite of whatever single input they were given. That's the whole. 3 kinds of gates, each one extremely simple, each one doing the small specific job that its name suggests. The thing that makes computers possible is that these 3 simple gates, when you wire enough of them together in the right patterns, can do anything. You can wire some of them together in a particular pattern to add 2 numbers. The pattern is not obvious, and the people who first worked it out had to think about it carefully, but once it exists, you have a small piece of circuitry that takes 2 numbers in the form of 2 patterns of ons and offs, and gives you the sum back, also in the form of ons and offs. If you want to multiply instead of add, you wire up a different pattern, with more gates. If you want to subtract, or divide, or compare 2 numbers to see which is bigger, you use a different pattern again. Every operation a computer performs is, at the bottom, a wiring pattern made of these 3 kinds of gates. The patterns get extremely complicated. The basic ingredients stay extremely simple. This is, in a sense, the second deepest fact about computers, after the fact that everything is bits. Every operation a computer performs, no matter how complicated it looks, is built up, ultimately, from a very small number of basic operations. The basic operations are the ones Boole described in 1854. The arrangement of those operations, the wiring diagram that turns simple gates into something useful, is the work of engineering. And the actual physical implementation of those gates, the question of what kind of switch you use to make the gates with, is the next part of the story. Because by the late 1940s, the electrical relays that Shannon had been working with in the basement had begun to seem clumsy and slow, and 3 men at Bell Labs were working on something better. Chapter 3: The 3 Men at Bell Labs. The Bell Telephone Laboratories in 1947 was an enormous research organization owned by the American Telephone and Telegraph Company. It occupied a sprawling collection of buildings in Murray Hill, New Jersey, and it employed several thousand scientists and engineers. Bell Labs' official mission was to improve the telephone network, but in practice, the laboratory funded research on almost any topic that its scientists found interesting. It had a reputation by the late 40s for being the best place in the United States to do basic scientific research outside of a university. In one of the buildings at Murray Hill in the winter of 1947, 3 men were working on a particular problem. The problem was that the vacuum tube, which was the main electronic switching device of the time, was no good. Vacuum tubes were the small glass bulbs, about the size of a person's thumb, that produced the warm glow visible inside old radio. Each tube contained, in a partial vacuum, a heated filament that boiled off electrons, and a few small pieces of metal that controlled the flow of those electrons in particular ways. A vacuum tube could function as an electrical switch. It could be turned on and off thousands of times per second by a small control signal. The early computers that had been built during and after the Second World machines like ENIAC at the University of Pennsylvania used vacuum tubes for their switching elements. ENIAC contained about 18,000 of them. Vacuum tubes had several problems. They generated a great deal of heat. They consumed a great deal of electricity. They were physically large, which meant that a computer with 18,000 of them filled a room. And they were unreliable. Each tube had a heated filament that would, eventually, burn out, the way an incandescent light bulb burns out. ENIAC was famously down for repairs more often than it was running, because at any given time some of its tubes were dead and needed to be replaced. The three men at Bell Labs had been trying since 1945 to invent a better switch. The official leader of the project was a physicist named William Shockley, who was tall, intelligent, and famously difficult to work with. Shockley had grown up in California, earned a doctorate at MIT, and joined Bell Labs in 1936. He had been thinking, for years, about whether the kind of switching that vacuum tubes did could instead be done by certain crystalline materials called semiconductors. Semiconductors were materials, mostly the elements silicon and germanium, that conducted electricity, but only partially. They were not as good at conducting as metals were. They were not as bad as insulators were. They were in between. The exact way that electricity moved through them depended, in interesting ways, on tiny impurities added to the crystal, and on small electrical fields applied from outside. Shockley had been assembling a team to work on the problem. The two men he chose to work most closely with were John Bardeen, who was a theoretical physicist, quiet and thoughtful, and Walter Brattain, who was an experimental physicist, hands-on and patient. Bardeen would think about what should happen. Brattain would build the experiments to find out whether it did. The three of them worked together through 1946 and 1947 in a small laboratory in Murray Hill. The work was slow and frustrating. Many of Shockley's theoretical predictions did not match the experimental results that Brattain produced. The team would build a small device, test it, find that it did not work, and have to figure out why. For most of the first 2 years, the answer to why it did not work was that nobody yet understood the precise behavior of electrons inside semiconductor crystals well enough to design a device that did what they wanted. On December 16, 1947, after many months of dead ends, Brattain and Bardeen built a small device that worked. The device was crude. It consisted of a small block of germanium with 2 thin gold foil points pressed against its top surface and a metal plate beneath. By varying the voltage on one of the gold points, the two researchers could control the flow of electricity between the other gold point and the plate. The control was strong. A small change in the voltage on the first point produced a large change in the current flowing between the other two contacts. The device, in other words, was an amplifier. It could also be operated as a switch, by applying enough voltage to fully turn the current on or off. What Bardeen and Brattain had built was the first transistor. The name had been coined a few weeks earlier by another Bell Labs scientist who had been looking for a term that suggested its dual role as a transfer resistor. The first transistor was a clumsy thing. Its gold foil contacts had been made by hand. The geometry of the device was awkward. It was, by the standards of any commercial product, almost useless. But it worked. It demonstrated that a piece of solid material, with no vacuum and no heated filament, could perform the same function as a vacuum tube. The implications were enormous, although it would take years for those implications to be fully appreciated. Shockley, who had not been in the lab on the day of the first successful test, was reportedly furious that his two colleagues had made the breakthrough without him. He spent the next few weeks on his own time working out a more elegant design for a transistor that would not require the awkward arrangement of gold foil points. The design he produced, which he called the junction transistor, was based on a different physical principle. It was a single piece of semiconductor crystal, with 3 different regions doped with different impurities arranged in a sandwich. The flow of current through the sandwich could be controlled by a small voltage applied to the middle region. The junction transistor would, over the next several years, replace Bardeen and Bretaigne's point contact transistor entirely, and would become the basic kind of transistor used in essentially every electronic device ever made. The relationship between the 3 men deteriorated rapidly after the invention. Shockley felt that he had not received enough credit for his theoretical contributions. Bardeen and Bratton felt that Shockley had taken too much credit for an invention they had made without. The 3 of them shared the 1956 Nobel Prize in Physics for the invention of the transistor, but they had stopped speaking to each other in any friendly way by then. Bardeen left Bell Labs in 1951 to join the University of Illinois, where he would later share a second Nobel Prize for a different piece of work, becoming, as of these recordings, the only person ever to win 2 Nobel Prizes in physics. Bratton stayed at Bell Labs, but moved to a different research group. Shockley left Bell Labs in 1955 to found his own company in California, which would, indirectly, become the seed of what is now called Silicon Valley. The story of Shockley's California venture is, in the history of computing, a small and strange one. Shockley had decided to set up his company near Stanford University, in a small town called Mountain View, partly because his elderly mother lived nearby in Palo Alto. He had recruited, through his connections, a small group of the most promising young semiconductor engineers in the United States, persuading them to leave their existing jobs and move to California to work with the famous inventor of the transistor. The young engineers arrived in 1956 with high hopes. What they found almost immediately was that Shockley was an extremely difficult person to work for. He was, by most accounts, brilliant but paranoid. He suspected his employees of conspiring against him. He set them to work on a particular kind of transistor design that several of them believed was technically misguided. He made them take lie detector tests when small things went missing in the office. He published the salaries of all his employees on the company bulletin board. Within about a year, a small group of his most talented engineers had become deeply unhappy. In September of 1957, 8 of those engineers walked into Shockley's office and resigned all at once. They became known in the history of the industry as the Traitorous 8. The 8 included men named Robert Noyce and Gordon Moore, who we will hear from again shortly. The 8, with funding from a New York investor, set up their own semiconductor company a few miles away. They called it Fairchild Semiconductor. Fairchild, over the next decade, became one of the most important companies in the early semiconductor industry. It produced, among other things, the planar manufacturing process that made the integrated circuit possible. Fairchild also, over the years, spun off many additional companies. Engineers who had worked at Fairchild left with their accumulated knowledge to start their own businesses. Some of those companies, in turn, spawned still more companies. The pattern of engineers leaving one semiconductor firm to start the next one became the defining characteristic of the area south of San Francisco. By the late 70s, The small region of orchards and farmland that the 8 original engineers had moved to in 1956 had been dramatically transformed. A journalist named Don Hoefler, writing in a trade magazine in 1971, had given the region the name that has stuck ever since. He called it Silicon Valley. Shockley, in some indirect way, by being such a difficult man to work for, had been the cause of the largest concentration of technology companies in human history. The transistor, over the following years, gradually replaced the vacuum tube as the basic switching element of electronics. By the early 1960s, transistors were small enough and cheap enough that even consumer products like radios were built around them. By the mid-60s, computers were being built using transistors instead of vacuum tubes. A computer that had once filled a room could now be built into a single cabinet. A computer that had cost millions of dollars could now be built for hundreds of thousands. The change in cost and size made computers, for the first time, things that ordinary businesses could afford to buy. What the transistor enabled, more than anything, was the implementation of Boolean logic at speeds and densities that nobody had previously imagined. A single transistor could be turned on and off millions of times per second. A circuit board the size of a paperback book could contain 100 transistors. A computer the size of a refrigerator could contain 100,000 transistors, and the logical operations those transistors performed were the same logical operations that Boole had described in 1854, and Shannon had connected to switches in 1937. The transistors were just much faster and much smaller than the relays Shannon had originally used. But 100,000 transistors in a refrigerator-sized computer was still, in 1958, expensive and bulky. The transistors had to be made one at a time. They had to be wired together by hand. The interconnections between them, on circuit boards, took up most of the physical space. The next step, the step that would make computers small enough to put on a desk and eventually small enough to put in a pocket, would be to figure out how to make many transistors at once, on a single piece with the connections between them already in place. That step would be taken by 2 different men, working independently in the summer and fall of 1958. Chapter 4, the summer everyone was on vacation. Jack Kilby was 34 years old in the summer of 1958. He was a tall, soft-spoken electrical engineer from Kansas. He had just been hired 3 months earlier by Texas Instruments, an electronics company in Dallas which had been making semiconductor products since the early 50s. As a new employee, Kilby had not yet earned any vacation time. So when the company, like many American companies of the time, closed for 2 weeks in July for what was called the summer shutdown, Kilby had nowhere to go. The other engineers had gone home or on family trips. Kilby was alone in the building. He decided, since he was there anyway, to think about a problem that had been bothering him. The problem was what people in the electronics industry called the tyranny of numbers. As electronic circuits became more complicated, they required more and more individual components, each of which had to be made separately and then wired together by hand. A typical electronic circuit in 1958 might contain a few dozen transistors, a few dozen resistors, a few dozen capacitors, and a great many small wires. Each component was the size of a pea or a grain of rice. Each connection between components had to be soldered. The reliability of the whole circuit depended on every component working and every soldered joint holding. As circuits got more complicated, the chance that some component or solder joint would fail somewhere went up. There was an upper limit, in 1958, on how complicated an electronic circuit could be before it became too unreliable to be useful. Kilby's idea, which came to him during those 2 weeks of summer shutdown, was a particular kind of solution to the tyranny of numbers. He wondered whether it might be possible to make all of the components of a circuit out of the same piece of material. Specifically, he wondered whether you could make a transistor and a resistor and a capacitor all out of the same piece of silicon by carefully choosing which impurities to add to which parts of the silicon. If you could do that, you would not need to wire the components together with separate wires. The components would already be inside the same piece of material. The connections between them could be made by depositing thin layers of metal directly onto the surface of the silicon. The idea was, in retrospect, simple, but almost no one had thought of it before. The standard approach in the electronics industry was to make each component as a separate physical object and then connect them. Kilby's approach was to make many components at once on a single piece of material with no separate connections needed. When the other engineers came back from vacation in late, Kilby went to his supervisor and described what he wanted to try. His supervisor was skeptical but agreed to let him build a prototype. Kilby spent the next several weeks at the bench working out the details. On September 12, 1958, he demonstrated the prototype. The device was a small sliver of germanium less than half an inch long, with a few wires bonded to its top surface. It contained, on a single piece of crystal, a transistor, a resistor, and a capacitor, all connected together to form a working oscillator circuit. It was the first integrated circuit. It worked. Kilby's prototype was awkward. The wires that connected the components to the outside world were still bonded by hand. The geometry was crude. But the proof of concept was there. You could make multiple components on a single piece of semiconductor material. A few months later, in January of 1959, an engineer at a different company had a related idea. The company was Fairchild Semiconductor, in Mountain View, California, which had been founded the year before by a group of engineers who had left Shockley's company because they could no longer tolerate Shockley's management style. The engineer at Fairchild was Robert Noyce, who was 31 years old, charismatic, and a gifted manager. Noyce had been thinking about the same tyranny of numbers that Kilby had been thinking about, although the two men did not know each other and had not communicated. Noyce's idea was similar to Kilby's, but with a critical improvement. Instead of bonding wires to the surface of the chip to make the connections, Noyce proposed that you could deposit thin layers of metal directly onto the surface in particular patterns to act as wires. The technique for doing this had recently been developed at Fairchild and was called the planar process. Using the planar process, you could make an entire circuit, with all its components and all its connections, in a single sequence of manufacturing steps. There would be no hand bonding of individual wires. The whole chip would be made by depositing layers of material onto a piece of silicon in patterns determined by precise photographic stencils. Noyce filed for a patent on his version of the integrated circuit in January of 1959. Kilby's company, Texas Instruments, had already filed for a patent on Kilby's version. The two patents covered overlapping but slightly different ideas. After several years of legal disputes, the two companies agreed to cross-license each other's patents, and the technique used in the rest of the industry would become a combination of Noyce's planar approach with some of Kilby's ideas about which components to integrate. The integrated circuit, over the next several decades, would become the basis of essentially all of modern electronics. The early integrated circuits in the early 60s contained a handful of transistors. By the late 60s, integrated circuits contained dozens of transistors. By the mid-70s, they contained thousands. By the 80s, they contained hundreds of thousands. By the 2000s, they contained millions. By the 2020s, the most advanced chips, the ones inside the most expensive phones and laptops, contained tens of billions of transistors, each one about 10 nanometers across, which is about 100 times smaller than the wavelength of visible light. What made this possible, more than anything, was a pattern that had been noticed in the mid-60s by Gordon Moore, one of the engineers at Fairchild who we met a few chapters back. Moore had noticed that the number of transistors that could be fit onto a single chip seemed to be doubling about every 2 years. He published the observation in 1965 in a trade magazine. The observation came to be called Moore's Law, although it was not a law in any scientific sense. It was just a pattern. Moore's Law continued to hold year after year, decade after decade, for over 50 years. The number of transistors per chip doubled, and doubled, and doubled again, until the chips were no longer made of the same kind of transistors at all, and the components had become so small they were approaching the size of individual atoms. The pattern began to slow down in the late 2010s, as the physics of making things smaller approached its limits, but by then the industry had built chips so dense, so fast, and so cheap that the world had been thoroughly transformed by them. The chip in the phone in your pocket, if you have one, is the latest descendant of Jack Kilby's little sliver of germanium. The phone's chip contains, depending on which phone it is, somewhere between 5 billion and 20 billion transistors, all manufactured at the same time on a single piece of silicon, with all the connections between them deposited as thin patterns of metal during the same manufacturing process. The cost to make the chip, for the manufacturer, is a few tens of dollars. It is, in terms of the number of individual functioning components packed into a physical object, by far the most complicated thing that human beings know how to build. But none of those billions of transistors do anything by themselves. They need to be arranged according to some plan that turns their combined activity into useful work. The arrangement of transistors that defines what a computer chip actually does, the architecture of the chip, is the subject of the next part of our story. And the basic design that almost every computer in the world still follows, 80 years after it was first sketched out, was worked out by a Hungarian mathematician in a hospital in Aberdeen, Maryland, in the spring of 1945. Chapter 5: The Architecture of the Machine. John von Neumann was 41 years old in 1945. He had been born in Budapest, the son of a wealthy banker, and had shown signs of being a prodigy from a very young age. He had memorized phone books for entertainment as a child. he had multiplied 4-digit numbers in his head by the age of 6. He had spoken 5 languages by the age of 10. He had earned a doctorate in mathematics by the age of 22. By his early 30s, he was widely considered to be one of the most extraordinary mathematicians of his generation. He had emigrated to the United States in 1930, joining the New Institute for Advanced Study in Princeton, New Jersey, where Albert Einstein and several other prominent European scientists had also gone. During the Second World War, von Neumann had been involved in many of the most important scientific projects of the war effort. He had worked on the Manhattan Project, the program to build the atomic bomb. He had worked on the mathematics of ballistics, calculating the trajectories of artillery shells. He had worked on the mathematics of explosives, designing the shaped charges that would be used in the bomb's implosion mechanism. He traveled throughout the war between Princeton and Los Alamos and the various other sites where his expertise was needed. There was, in the years just before the war, another mathematician who had also been thinking about computation in a very different way on the other side of the Atlantic. His name was Alan Turing. He was English, born in 1912, and he had been a graduate student at Cambridge in 1936 when he wrote a paper that would in retrospect become the theoretical foundation of computer science. The paper was titled On Computable Numbers, and it was an attempt to answer a question about the limits of mathematical reasoning. The question, posed by the German mathematician David, was whether there was a precise mechanical procedure that could determine, for any mathematical statement, whether the statement was true. To answer this question, Turing had to define what was meant by a mechanical procedure. He did so by inventing, on paper, a kind of imaginary machine. The machine was extremely simple. It consisted of a long paper tape divided into squares on which symbols could be written. There was a small head that could read the symbol on the current square, write a new symbol, and move the tape one square to the left or right. The behavior of the head was governed by a simple set of rules. Depending on what symbol it saw and what internal state it was in, it would write a new symbol, change its state, and move. That was all. There was nothing else to the machine. Turing showed, in his paper, that this simple machine could be programmed by an appropriate choice to perform any mathematical computation that any human being could perform on paper. The machine was, in some sense, the essence of computation, stripped down to its most basic form. The paper also showed something more surprising. There existed, Turing proved, a particular machine that could simulate any other machine, given an appropriate description of that other machine encoded on its tape. He called this the universal machine. The universal machine was a single device that could, given the right inputs, behave like any specific device. The same machine could compute square roots one moment and play chess the next, depending only on the rules written on its tape. What Turing had described, without quite meaning to, was the modern computer. The universal machine, with its rules read from a tape, was the abstract version of what von Neumann would design 10 years later as a real electronic machine, with its program stored in memory alongside its data. The two ideas were essentially the same idea, arrived at in different decades by different people working on different problems. Von Neumann, who had read Turing's paper, was almost certainly influenced by it when he wrote the first draft. Turing himself, during the war, had worked at the British code-breaking facility at Bletchley Park, where he had helped design machines that broke German codes. After the war, he had worked on the design of an early British computer called the Ace. His career was cut short. He was prosecuted under British law in 1952 for being gay, sentenced to chemical castration as an alternative to prison, and died in 1954 at the age of 41 of cyanide poisoning in what was officially ruled a suicide. The British government formally apologized for his treatment in 2009 and granted him a posthumous royal pardon in 2013. His face has been on the Bank of England's £50 note since 2021. In 1944, on a train platform at the station in Aberdeen, Maryland, von Neumann happened to meet a mathematician named Hermann Goldstein, who was working on a project at the University of Pennsylvania. Goldstein, in conversation, mentioned that the project he was working on involved building a very large electronic calculating machine. The machine was called ENIAC, which stood for Electronic Numerical Integrator and Computer. It was being built to perform ballistics calculations for the Army, the same kind of calculations that von Neumann had been doing by hand. Von Neumann, who had not previously heard of ENIAC, became interested. He arranged to visit the project. He began to participate in its design discussions. What von Neumann saw at the University of Pennsylvania was a machine that filled a large room. ENIAC contained, as we mentioned earlier, about 18,000 vacuum tubes, several thousand relays, and many miles of wire. It could perform about 5,000 additions per second, which was at the time an astonishing speed. But ENIAC had a particular limitation that von Neumann immediately noticed. The machine had no way to store a program in its memory. The way you told ENIAC what to do was by physically rewiring it. To run a new calculation, the operators had to spend days unplugging cables and plugging them in different configurations. The calculation itself, once the machine was configured, would run quickly. But the configuration was a manual process and a complicated one. Von Neumann began to think about how this limitation might be overcome. In the summer of 1945, he wrote a draft of a paper that laid out a different way of designing a computer. The paper was eventually titled First Draft of a Report on the EDVAC. EDVAC, which stood for Electronic Discrete Variable Automatic Computer, was the planned successor to ENIAC. The first draft was about 101 pages long, written entirely by von Neumann in his characteristic style, which was clear and precise and unusually accessible for a mathematical document. What von Neumann proposed in the first draft was a design that, with various refinements, would become the basic design of every computer built in the next 80 years. The design had a few key features. First, the program that the computer would run would be stored in the computer's memory, alongside the data the program would operate on. The program would not be encoded by physical wires. It would be encoded as a sequence of numbers, exactly like the data. The computer would, in effect, have no built-in idea of what it was for. It would just be a general-purpose machine that could be programmed to do anything, simply by loading the right program into memory. Second, the computer would have a small number of distinct parts, each with a specific role. There would be the memory, which stored both the program and the data. There would be the arithmetic unit, which performed the actual computations. There would be the control unit, which read the program from memory, one instruction at a time, and told the arithmetic unit what to do. There would be the input and output devices, which let the computer receive information from the outside world and send information back out. These four parts would be connected to each other by wires that carried data and signals between them. Third, the computer would do its work by following a simple loop. The control unit would look in memory for the next instruction. It would read the instruction and figure out what it was asking for, which might be adding two numbers or moving data from one place to another or checking whether two numbers were equal. It would do whatever the instruction said. Then it would go back to memory for the next instruction and do that one, and the next, and the next. The whole life of the computer would be this loop, repeated very fast, with the program telling the machine what to do at every step. This loop of getting an instruction, working out what it means, and acting on it is sometimes called the fetch, decode, execute cycle in technical writing. The everyday version of the name is just the instruction cycle. Every computer ever made since the mid-1940s has worked, deep down, by doing some version of this loop. The chip in the phone in your pocket is doing some version of it as you listen to these words, billions of times per second. The instructions it executes are themselves stored in memory alongside the data it operates on. The arrangement of memory, arithmetic unit, and control unit is recognizably the same arrangement von Neumann sketched in his hospital draft. The first draft of the EDVAC was, in retrospect, the founding document of computer architecture. It was, however, controversial in one specific way. Von Neumann's name was the only one on the document, even though several of the engineers at the University of Pennsylvania, particularly J. Presper Eckert and John Mauchly, who had designed ENIAC and were planning EDVAC, had contributed many of the ideas in. The Pennsylvania engineers felt with some justification that von Neumann had taken credit for work that was partly theirs. The dispute over credit would continue for decades, and would eventually lead to legal cases over patent rights, which would mostly be resolved in favor of the broader argument that the ideas in the first draft were too widely held to be the property of any single person. The design that von Neumann sketched is now usually called the von Neumann architecture, regardless of who deserves credit for which specific piece of it. It has variants and refinements, but its basic structure is what computers have been doing ever since. The processor reads instructions from memory and acts on them. The instructions, written in a precise language called machine code, tell the processor exactly what to do, one step at a time. Add this number to that number. Move this value into that location. Compare these two numbers, and if they're equal, jump to a different point in the program. The full set of available instructions, the instruction set, varies from one kind of processor to another, but the basic flavor is always similar. A computer is a thing that reads numbers, interprets them as instructions, and acts on them, one after another, very fast. The speed at which this happens in a modern computer is the thing that's perhaps hardest to appreciate. A modern processor performs the fetch, decode, execute cycle several billion times per second. Each cycle, the processor might add two numbers, or move a value from one location to another, or compare two values, or jump to a different part of the program. In the time it takes you to blink, a modern processor has performed several 100 million of these tiny operations. The work it does, on any given day, is the sum of an enormous number of very small steps, each of which is one of the basic operations von Neumann described in his first draft. For all of this to work, there has to be a place to put the program and the data. There has to be memory, and the memory has to be fast enough to keep up with the processor that is reading from it billions of times per second. The problem of building fast and reliable memory was, for the first decade of the computer age, one of the most difficult problems in the whole field. The story of how it was eventually solved involves a man at MIT, a flight simulator, and a small ring of magnetic material. Chapter 6A, Small Ring with a Question. J. Forrester was 30 years old in 1948. He had grown up on a cattle ranch in Nebraska, gone to MIT for graduate school, and had stayed on after the war as a research engineer. The project he was leading in 1948 was called Whirlwind. The goal of Whirlwind was to build a computer that could be used as a real-time flight simulator, allowing pilots to practice flying without actually being in an airplane. The Navy was funding the project, and the Navy needed a machine that could respond to a pilot's control inputs and update a simulated flight situation many times per second. Whirlwind ran into a particular problem early on. The computer needed memory, the place to store the program and the data the program was working with. The memory technologies available in the late 40s were not good. They were slow, or they were unreliable, or they were both. One option was to use vacuum tubes, where each bit of memory was represented by the state of a small electronic circuit. This worked but consumed enormous amounts of power. Another option was to use a system called mercury delay line, in which data was encoded as patterns of sound waves traveling through tubes of mercury. This worked, but was extremely fragile and difficult to read from. Another option was to use a kind of cathode ray tube called a Williams tube, in which data was stored as patterns of charge on the inside of a glass screen. This worked, but was unreliable in ways that made debugging difficult. For Whirlwind, none of these options was good enough. The flight simulator needed memory that was fast and reliable and could handle the demands of real-time operation. Forrester, in 1949, started thinking about whether there might be a different way of building memory entirely. The idea he eventually had came from looking at small rings of magnetic material called ferrites. Ferrites were ceramic compounds that could be magnetized in either of two opposite directions, and that would hold their magnetization stably once it was set. A small ferrite ring about the size of the head of a pin could be magnetized clockwise or counterclockwise by passing a current through a wire that ran through the middle of the ring. By passing a current in the opposite direction, you could flip the magnetization to the other orientation. The two orientations of magnetization could represent the two values of a bit. One direction could be a 0. The other could be a 1. Forrester realized that if you arranged many such rings into a grid, with horizontal and vertical wires running through them, you could read and write any individual ring by passing currents through the appropriate horizontal and vertical wires. The currents had to be strong enough, when combined at a single ring to flip its magnetism, but weak enough individually that they would not affect any of the other rings the wires passed through. The arrangement, when worked out carefully, would let you store a great many bits in a small physical space and access any individual bit quickly. Forrester, along with several MIT colleagues, including a graduate student named Bill Papian, spent 1949 and 1950 working out the details. The first working prototype of what came to be called magnetic core memory was built in 1953. It consisted of a square of 32,000 small ferrite rings, threaded onto a grid of wires by hand, with a small electronic circuit attached to each row and column to read and write the bits. It worked. It was fast. It was reliable. It would, over the next 2 decades, become the standard memory technology used in nearly every computer in the world. The threading of the rings in the early days was done by hand. The work required a great deal of patience and good eyesight, because each ring was the size of a pinhead and had to be threaded onto 4 separate wires. Much of the work was done by skilled female workers in dedicated factories, some of which were in the United States, and some of which were in countries with lower labor costs. A typical computer's memory bank in the 1960s contained millions of rings, threaded by hand, 1 ring at a time, by people whose names are mostly not recorded. Core memory remained the dominant memory technology until the early 1970s, when it began to be replaced by semiconductor memory, which used the same kind of transistors as the rest of the computer chip to store bits. Semiconductor memory was faster than core memory, cheaper to manufacture once the manufacturing process was established, and did not require the labor-intensive hand threading. By the late 70s, core memory was obsolete. The companies that had manufactured it switched to other products. The factory. What is interesting about the story of memory, beyond the specific technologies, is that the memory inside a modern computer is not a single thing. It is a stack of different kinds of memory, arranged in layers, each one faster but smaller than the layer below it. The arrangement is a bit like the way an office worker uses a desk. The papers you are actively writing on are right in front of you. The folders you might need soon are within arm's reach in a tray on the desk. The folders you need less often are in a filing cabinet across the room. The folders you almost never need are in a storage box in the basement. Each layer is bigger and farther away than the layer above it. You pull things up to the desk when you need them, and you put them back down when you are done. At the top of the stack, closest to the processor, are what are called registers. The registers are a small number of memory slots built directly into the processor itself. A typical processor has a few dozen of them. Each one can hold a single number of a particular size and can be read or written in less than a billionth of a second. The registers are the fastest memory the computer has. They are also the smallest. The processor can only hold a handful of values in the registers at any given moment. Beneath the registers is a layer called cache memory. Cache memory is also built into the processor chip, but it is larger than the registers and slightly slower. A typical modern processor has several megabytes of cache memory arranged in a few sublayers, each layer larger and slower than the previous one. The purpose of cache memory is to hold copies of data the processor is likely to need soon, so that the processor does not have to reach out to the main memory every time it needs something. Beneath the cache is the main memory, which is what most people mean when they say a computer has, for example, 8 gigabytes of memory. The main memory is made of semiconductor chips that sit on a circuit board near the processor. It is much larger than the cache, but slower to access. A typical computer has a few gigabytes of main memory, which is enough to hold the active programs and the data they are currently working with. Beneath the main memory is the long-term storage, which is where the computer keeps things even when the power is off. Storage was once made of magnetic disks, the kind of disks that spun and were read by a small arm holding a magnetic head. Storage is now mostly made of solid-state drives, which use semiconductor chips like the main memory, but designed to hold their values even when there is no electricity flowing through them. A typical computer has a few hundred gigabytes or a few terabytes of storage, which is enough to hold all the programs and files the user has ever created or downloaded. The hierarchy works because at any given moment, the processor is using only a small amount of data, and that data tends to live near other data the processor will need soon. The fast little layers at the top can hold the working set of data. The slow big layers at the bottom can hold everything else. As the processor works, data is moved up and down the layers pulled up from storage into main memory when a program is launched. Pulled up from main memory into the cache when a particular piece of data is needed. Pulled up into the registers when the processor is about to use it. The whole choreography is handled by a combination of the hardware and the operating system, in ways that the user never sees and almost never thinks about. J. Forrester, by the way, who invented core memory in 1949, lived for another 70 years after that invention. He went on to a long second career in management and in the mathematical study of how complicated systems behave over time. He died in 2016 at the age of 98, having seen the memory technology he invented be used, and then made obsolete, all within his lifetime. Chapter 7. The Navy officer who taught machines to speak English. The memory holds the program, but the program has to be written. The way that programs are written has changed enormously over the 80 years since the first stored program computers were built. The story of how it changed is, in many ways, the story of one particular person, a Navy officer named Grace Hopper, who spent 30 years arguing that computers should be able to understand instructions written in something closer to ordinary English. Grace Hopper was born in New York City in 1906, the eldest of 3 children. Her father was an insurance executive, her mother was a mathematician by inclination who had not been able to pursue mathematics professionally because of the limitations placed on women's careers in her generation. Hopper had been encouraged by both parents to study what she liked, and she had liked mathematics. She earned a bachelor's degree at Vassar in 1928, a master's degree at Yale and a doctorate at Yale in 1934, all in mathematics. She joined the faculty at Vassar after that and taught there for a decade. When the United States entered the Second World War, Hopper, who was then in her late 30s, tried to enlist in the Navy. She was rejected initially because she was too old and too underweight. She was accepted on her second try in 1943 into the Navy's Women's Reserve, called Waves. After training, she was assigned in 1944 to a project at Harvard University. The project involved a large electromechanical computer called the Mark I, which had been built at Harvard with funding from the Navy and IBM, and which was being used for various wartime calculations. The Mark I was, in some ways, a computer of the kind we have been describing. It used electrical switches and relays to perform calculations. It could be programmed by punching holes in a long paper tape, which the machine would read sequentially, one instruction at a time. Hopper, in 1944, was assigned to figure out how to program it. She had to teach herself, from the manual, what each of the available instructions meant, how to combine them into useful sequences, and how to debug the inevitable mistakes. It was during her time at Harvard that Hopper, by her own later account, became frustrated with the way programs were written. The instructions for the Mark I had to be written in what was, essentially, the machine's own numerical language. Each instruction was a small number that referred to a specific action the machine could perform. Programming the machine, in this language, was like writing a long sequence of cryptic codes. Each code had to be looked up. Each combination had to be carefully worked out. A small mistake anywhere in the sequence could cause the whole program to do the wrong thing, or nothing at all, with no clear indication of what had gone wrong. The frustration came to a head. For Hopper, when she realized that the same kinds of mistakes were being made by every programmer on every machine in every project. The programs that people wrote tended to do many of the same things over and over. They added numbers. They moved data from one place to another. They tested whether a value was greater or less than another value. They jumped to a different point in the program based on the result of a test. The actual variety of operations in any given program was small. The variety came from how the operations were combined. Hopper, after the war, had stayed in the Navy Reserve and joined a small private company called Eckert-Mauchly, which had been founded by two of the engineers who had built ENIAC. The company was building, in the late 40s, one of the first commercial computers called UNIVAC. Hopper was hired to work on the programming. While she was there, she began to develop the idea that would shape the rest of her career. The idea was that, instead of writing programs in the machine's own numerical language, you should be able to write them in something closer to ordinary English. You should be able to type a command like add A to B, and the machine should understand. The machine, of course, did not understand English. The machine only understood its own numerical language, but a special program, called a compiler, could translate the English-like commands into the numerical language. The compiler would read the human-friendly text, look up what each command meant, and produce the corresponding sequence of machine instructions. The human programmer would write in a language designed for humans. The compiler would translate it into a language designed for machines. Hopper wrote the first compiler in 1952. It was called AERO. It was crude and limited. It could only translate a small number of commands, but it worked. It demonstrated that the translation between human-friendly text and machine instructions could be automated. The idea was, at first, resisted by many of the senior people in the small computing industry of the early 1950s. Computers in those years were extremely expensive. The cost of each second of computer time was very high. The idea of using some of that valuable computer time to translate human friendly text into machine instructions, when a skilled programmer could write the machine instructions directly, struck many people as wasteful. Hopper, by her later account, had to spend a great deal of time persuading people that the trade-off was worth it. The compiler would be slow. The programs it produced would not be as efficient as programs written by hand. But the programs would be written much faster. Programmers would make fewer mistakes. The same program would be readable by a different programmer 6 months later, in a way that handwritten machine instructions usually were not. Over the course of the 1950s, the idea of compilers gradually won. In 1954, a team at IBM, led by a programmer named John Backus, began developing a language called Fortran, which was intended for scientific calculations. Fortran was the first widely successful higher-level programming language. It was followed in 1959 by a language called COBOL, which was intended for business applications and which Hopper had been one of the major designers of. COBOL was deliberately designed to read like English. A line of COBOL code might say, "Add customer payment to account balance." The intent was that a person who was not a programmer could read a COBOL program and understand, more or less, what it did. After Fortran and COBOL came many other languages. Each one was designed for some particular purpose, or with some particular philosophy, or with some particular improvement on its predecessors. Some of them have come and gone over the years. Some of them are still used today. The major programming languages of the modern era, languages with names like C, C++, Java, Python, JavaScript, and Rust, are all the descendants of the original idea that Hopper had at Eckert-Mauchly in 1952. They all let programmers write text that is reasonably readable by humans, and they all rely on a compiler or a similar program to translate that text into the machine's own numerical language. A modern programmer, in the 2020s, writes code in a language like Python. The code looks like a sequence of mostly English commands. Read this file. Loop through every line of the file. If the line contains a particular word, save it somewhere. When all the lines have been processed, write the saved lines to another file. The programmer types these commands into a text editor. When the program is ready to be run, the computer runs a piece of software, the Python interpreter, which reads the program and translates each command into the corresponding sequence of machine instructions and then sends those instructions to the processor. The processor, of course, does not know that it is running a Python program. The processor only knows that it is executing the basic operations from its instruction set, the operations that von Neumann described in his first draft. The translation from the Python program to the actual instructions the processor executes is happening invisibly in the background. The chain that connects what the programmer writes to what the processor does is several layers deep. The programmer writes in Python. The Python interpreter translates the Python into a lower-level language. The lower-level language is translated into machine code. The machine code is fed to the processor, one instruction at a time. The processor performs the fetch-decode-execute cycle billions of times per second on instructions that came, originally, from a programmer typing English-looking text into an editor somewhere. Grace Hopper, who started this whole chain in 1952, retired from the Navy in 1986 at the age of 79 as the oldest active duty officer in the United States Navy at that time. She had been promoted to the rank of Rear Admiral. She gave lectures into her 80s on the importance of teaching computers to speak languages that humans could read. She died in 1992 at the age of 85. She was given a full military burial at Arlington National Cemetery. The United States Navy has named 2 destroyers after her since. Chapter 8: The Middleman That Runs Everything. A computer that can run programs is, by itself, not yet a useful computer. There is a missing piece. The missing piece is the program that manages all the other programs. The thing that lets you have many programs available on the same machine and switch between them and use them in combinations and have them not interfere with each other. The thing that when you turn the machine on sits there waiting for you to tell it what to do. This thing is called the operating system, and it is in many ways the most important piece of software on any computer. The story of operating systems, like the story of programming languages, is long and full of competing systems that have come and gone. But there is one particular operating system whose history is worth telling in detail, because it is the ancestor in one way or another of almost every operating system that is now in use. The operating system is called Unix, and it was created at Bell Labs in New Jersey in 1969 by 2 researchers named Ken Thompson and Dennis Ritchie. Thompson and Ritchie were, at the time, in their late 20s and early 30s. They had been working, with a larger team, on a much more ambitious operating system project called Multics, which had been a joint effort between Bell Labs, MIT, and General Electric. Multics had been intended to be a kind of universal computing utility, a system that many users could share at the same time and that would provide all of the services they could need. The project had run for several years and had produced a working system, but it was complicated and slow, and Bell Labs' management had concluded that it was not worth continuing. In 1969, the company pulled out of the Multics project. Thompson, who had been one of the Bell Labs programmers on the Multics team, was disappointed. He had liked the ideas of Multics. He missed the working environment it had provided. He had also, during the project, written a small video game called Space Travel, which let the player fly a small spaceship through a simulation of the solar system. Thompson had been playing the game on the Multics system. With Multics gone, he had no good machine to play it on. He found an unused computer in a corner of the Bell Labs building, a small mini-computer called a PDP-7 made by Digital Equipment Corporation. The PDP-7 had a screen and a keyboard and was, by the standards of the time, modestly capable. Thompson decided to port his game to the PDP-7. As he started this work, he realized that he would also need some basic software infrastructure on the PDP-7 to make the work feasible. He would need a way to manage files on the machine's storage. He would need a way to compile programs. He would need a way to run programs and interact with them. In the absence of all of this, he would have to write it himself. Thompson, in the late summer of 1969, sat down and wrote, more or less by himself, the first version of an operating system that would later be called Unix. The name, by some accounts, was a joke. Multics had been pronounced multi-ix in reference to multiple users. Thomson's small system supported only a few users at a time, often just one. So it was Unix. Unix, the first Unix, was, by modern standards, primitive. It had a file system which let you store and retrieve files by name. It had a small collection of programs that could be run from a command line. It had a simple way of running multiple programs at the same time and switching between them. It was not designed to be a serious product. It was designed to be useful enough to let Thomson port his video game. But other people at Bell Labs noticed Unix and started using it themselves, and started suggesting improvements. Dennis Ritchie, who shared an office with Thomson, became deeply involved in the project. Ritchie, who was the more linguistically inclined of the two, designed a programming language called C in the early 70s, which became the language Unix was written in. The combination of C and Unix turned out to be, in retrospect, one of the most important pairings in the history of computing. Unix could be moved from one kind of computer to another by recompiling its C source code, which meant that Unix could run on essentially any computer that had a C compiler. The set of computers that had C compilers grew over the years to include essentially every computer made. What an operating system actually does, in the version that Thomson and Ritchie developed and that has been refined over the decades since, is a few specific things. It manages the hardware of the computer, hiding the details from the programs that run on top of it. A program that needs to read a file does not need to know what kind of storage device the file is on. It just asks the operating system for the file, and the operating system handles the rest. A program that wants to display something on the screen does not need to know what kind of screen is attached. It just sends the image to the operating system, and the operating system figures out how to put it on the actual screen. The operating system also manages the simultaneous execution of multiple programs. A modern computer is almost always running many programs at the same time. The web browser is running. A word processor is running. Some background processes are running that handle things like email notifications and system updates. The operating system gives each of these programs a small slice of the processor's time, switching between them rapidly enough that they all appear, to the user, to be running at the same time. The switching on a modern processor happens thousands of times per second. The operating system also manages the boundaries between programs. Each program runs in what is called a process, which is a sort of bubble inside which the program operates. Within its bubble, the program has access to its own memory and its own files. It cannot directly affect the memory of other programs. It cannot directly modify the files of other programs. If it wants to communicate with another program, it has to go through the operating system, which mediates the conversation. This isolation is what keeps a misbehaving program from crashing the entire computer. If a web browser, say, has a bug and crashes, the operating system notices that the browser process has died and reclaims its memory. The other programs on the system are unaffected. The operating system also handles security. It enforces the rules about which users can access which files, which programs can be run, which programs can access which network resources. The whole structure of permissions and accounts and passwords that you experience as a user is implemented by the operating system. When you log in with a password, The operating system is the thing that checks the password against its records. When a program asks to read your files, the operating system is the thing that checks whether the program has permission. Unix, over the decades since 1969, has spawned an entire family of operating systems. The most direct descendant is a system called Linux, which was created in 1991 by a Finnish university student named Linus Torvalds, who had been frustrated that the various commercial versions of Unix were too expensive for ordinary users. Torvalds wrote a Unix-compatible operating system from scratch in his spare time and released the source code for free on the Internet. Linux became, over the next 30 years, the dominant operating system for servers, supercomputers, and most of the hardware that runs the Internet itself. It is also, in modified form, the operating system that runs Android phones. About 3 billion Android phones are currently in use, all running an operating system that started, in some sense, when a Bell Labs programmer in 1969 wanted somewhere to play his spaceship game. The other major modern operating system, called macOS, which runs Apple's computers, and which has a closely related variant called iOS that runs Apple's phones, is also a descendant of Unix. macOS was built, in the late 1990s, on top of a system called NextStep, which Steve Jobs' company NeXT had developed when he was away from Apple. NextStep was built on top of a version of Unix called BEST, which had been developed at the University of California at Berkeley in the late 70s. The chain of inheritance from Thomson and Ritchie's original Unix to the operating system on a modern Macintosh is direct, if long. The operating system that is the major exception to all this, which is Microsoft Windows, has its own separate history. Windows began in the mid-1980s as a graphical layer on top of Microsoft's earlier text-based operating system, DOS, which had been licensed to IBM for the original IM personal computer. Modern versions of Windows are descendants of a different family entirely, called Windows NT, which was developed in the early 1990s and which has always been distinct from the Unix family, although the two families have, over the years, gradually adopted many of the same ideas. What is on your screen right now, if you are listening to this on a phone or a computer, is the result of an operating system doing all of the things we have just described. It is managing the hardware. It is running many programs at the same time. It is keeping them from interfering with each other. It is enforcing security. It is mediating between the programs and you. The operating system is, in some real sense, the most active piece of software on the machine. Even when no other program is running, the operating system is still working, somewhere in the background, doing the small constant tasks that keep everything else going. Chapter 9: The World Coming into the Box. So far, we have mostly been talking about what happens inside the computer. The processor doing its fetch-decode-execute cycle, the memory holding the program and the data, the operating system managing it all. But none of this is useful without a way for the computer to interact with the world outside itself. A computer that could not receive any input from a human and could not produce any output that a human could see would be, no matter how powerful, useless. The story of how computers came to interact with the world is the story of what are called input and output devices, or for short, I/O. In the earliest computers, the I/O devices were extremely primitive. The input was a stack of punched cards, which had been prepared on a separate machine called a key punch, by typing the program on a typewriter-like keyboard that would punch the corresponding holes into a thick paper card. Each card held about 80 characters worth of information. A program of any substantial size would require a stack of hundreds or thousands of cards. The cards were fed into the computer by a card reader, which mechanically pulled them through one by one and detected the holes by shining light through them. The output was usually a printout, produced by a line printer that would type the results of the computation onto continuous paper. The cycle of programming for a programmer of the 1950s or 60s was to write out the program by hand, take it to the key punch room, type each line onto a card, take the stack of cards to the computer center, submit the stack to the operator, wait some hours, and then collect the printout to see whether the program had worked. Each cycle could take a day or more. In the 1960s, things began to improve with the introduction of teletype terminals. A teletype was essentially a typewriter connected to a computer. The user could type commands at the keyboard which would be sent to the computer, and the computer's responses would be typed back by the same teletype onto a roll of paper. Teletypes were noisy and slow, but they let the programmer interact with the computer directly, without going through the punched cards and the printouts. The development of teletypes meant that, for the first time, a programmer could see the results of a command within seconds rather than within hours. In the 1970s, teletypes began to be replaced by video terminals, which displayed the text on a screen instead of typing it onto paper. A video terminal was electrically similar to a teletype, but it used a cathode ray tube to display text in glowing letters on a dark glass screen. Video terminals could refresh the screen quickly, which made it possible to do new kinds of interaction. A program could update the same part of the screen many times per second, which meant that you could write programs that showed continuously changing information, or that responded to keystrokes in real time, or that displayed simple animations. The video terminal was, in many ways, the direct ancestor of the screen on every modern. In the 1980s, with the introduction of the personal computer, the input and output devices became more elaborate. The keyboard remained the main input device for typing text, but a new device, the mouse, became standard. The mouse had been invented in the 1960s at the Stanford Research Institute by an engineer named Douglas Engelbart, but had not become widely used until the personal computer era. Engelbart, whose name is worth pausing on for a moment, is one of the more remarkable figures in the history of computing. He had grown up on a small farm in Oregon, served in the Pacific during the Second World War, and had read, while waiting to be discharged, an article by Vannevar Bush, the same Vannevar Bush who had built the differential analyzer at MIT that Claude Shannon had worked on about a hypothetical machine called the Memex, which was supposed to help people think by letting them store and connect information. The article had struck Engelbart deeply. He had spent the following years working on a doctorate in electrical engineering and then taking a research position at the Stanford Research Institute, where he set up a small laboratory with the explicit goal of augmenting human intellect with computers. Throughout the 1960s, Engelbart and his small team worked on a system they called the Online System, or NLS. NLS was in many ways a vision of what personal computing could be that was decades ahead of its time. It included the mouse which Engelbart had invented in 1964 with a colleague named Bill English. It included windows on the screen. It included hypertext links between documents. It included the ability for multiple users at different locations to collaborate on the same document at the same time over a network. It included video conferencing. On December 9, 1968, in a hall at the Joint Computer Conference in San Francisco, Engelbart gave a public demonstration of NLS. The demonstration lasted 90 minutes. Engelbart sat on a stage with a custom-built workstation while a remote system at SRI sent text and graphics to a large screen behind him. He showed, on stage, almost every feature of what we now think of as a modern personal computer. He showed how to point at things with a mouse. He showed how to insert and edit text in a document. He showed how to create links between different documents. He showed how to share a screen with a colleague at a different location. He showed how to make a video call. The audience, which consisted of about 1,000 computer professionals, mostly sat in stunned silence. Many of them had never seen any of these things before. The demonstration came to be known, in the years afterward, as the mother of all demos. Almost nothing that Engelbart showed in 1968 became commercially available until the 1980s or 1990s. The mouse, in particular, sat unused by the industry for over a decade after his demonstration, until Apple included it on the Lisa in 1983 and on the Macintosh in 1984. Engelbart himself spent most of the years after his famous demonstration working on refinements of NLS, watching, with what must have been a particular kind of patience, as the ideas he had demonstrated gradually entered the mainstream over the following decades. He died in 2013 at the age of 88. The mouse had, by then, become so common that nearly every computer in the world had one or had something derived from it. The list of his other inventions, most of which had been part of NLS, had also become standard features of nearly every computer. The mouse let the user point at things on the screen, which was a much more natural way to interact with graphical interfaces than typing commands. The screen itself, in the personal computer era, became capable of displaying images and colors and arbitrary graphics, in addition to text. In the years since the personal computer became common, the list of input and output devices has continued to grow. Touch screens on phones and tablets let the user point directly at the screen with a finger. Cameras let the computer see. Microphones let the computer hear. Speakers and headphones let the computer talk. Printers, scanners, network connections, USB drives, external hard drives, fingerprint sensors, accelerometers, GPS receivers, all of these are I/O devices. Each one extends the computer's ability to interact with the world in some particular way. What ties all of these devices together, from the punched cards of the 1950s to the touch screens of today, is a piece of software called a driver. A driver is a small program that knows how to talk to a particular piece of hardware. When the operating system needs to send something to a printer, for example, it does not need to know the specific electrical signals that the printer expects. It just sends a request to the printer's driver, which converts the request into the electrical signals. When a key is pressed on the keyboard's driver translates the electrical signal from the key into a number that represents which key was pressed, and passes the number to the operating system. The drivers in a modern computer are how the operating system manages the immense variety of hardware that can be connected to the machine. Without drivers, the operating system would have to know, intimately, the workings of every possible device. With drivers, the operating system only needs to know about devices in general, and each specific device is described to the operating system by its own driver. This is part of why, when you plug a new device into a computer, the computer often has to install some software before the device will work. The software it installs is the driver. Most of the time, the I/O devices on a computer work without the user ever thinking about them. You type, and characters appear. You move the mouse, and the cursor moves. You speak, and the microphone picks up your voice. The computer's response to these inputs feels immediate. In reality, every keystroke and every mouse movement and every word of audio triggers a small chain of events. The hardware generates an electrical signal. The driver translates the signal into something the operating system understands. The operating system delivers the information to the appropriate program. The program does something in response. The result is sent back through the operating system, through the driver, to the appropriate output device. The whole chain typically takes a few thousandths of a second. This chain is so quick and happens so often that the computer's job, when you actually look at it from the right angle, can be described almost entirely as the job of moving information through these chains. The processor's fetch-decode execute cycle is the engine. The memory holds the data. The operating system runs the show. But the actual work that the computer does, the thing that you can see and use, is the constant flow of information into the machine through the input devices, and out of the machine through the output devices, mediated by everything we've talked about tonight. There is one final thing worth understanding before we walk through this whole machine in action. It has to do with what happens, in a more detailed way, when a key is pressed on a keyboard. The walkthrough, the story of one keystroke from start to finish, brings together everything we have talked about, and it is in some way the best way to feel how the whole machine actually fits together. Chapter 10: What happens when you press a key. We have by now walked through most of the major pieces of how a computer works. The bits, the logic gates, the transistors, the integrated circuits, the von Neumann architecture, with its processor and its memory and its instruction cycle, the memory hierarchy from the fast small registers down to the slow large storage, the programming languages and the compilers that translate them into instructions the processor can run, the operating system which manages everything, the input and output devices which connect the machine to the world. To make the picture complete, it helps to walk through what actually happens, in some detail, when you do something simple on the computer. Let's say the computer is on, an application is open, and you press a single key on the keyboard. Let's say you press the letter A. From your perspective, almost nothing visible happens, except that, after a tiny moment, the letter A appears on the screen in whatever application you are working with. From the computer's perspective, the following sequence of events has taken place, in something like a few thousandths of a second. The key on the keyboard, when you press it, completes an electrical circuit. The keyboard is, electrically, a grid of contacts. Each key, when pressed, connects one specific row to one specific column. The keyboard has inside it a small dedicated processor whose only job is to scan this grid many hundreds of times per second, looking for changes. The dedicated processor is itself a small computer, with its own little program running on it, made of the same kinds of transistors as the main processor in the computer. When the dedicated processor detects that the row-column intersection corresponding to the A key has just been completed, it knows that you have just pressed that key. It generates a small message, in the form of a sequence of bits, that identifies the key that was pressed. The message is sent through a small wire or a wireless connection to the main computer. If the keyboard is plugged into the computer through a USB cable, the message is encoded according to the rules of the USB protocol, which specify exactly how bits should be transmitted along the wire. The bits arrive at a small chip inside the computer called a USB controller. The USB controller is, again, a small dedicated processor. It receives the bits, decodes the USB protocol, extracts the message about the key that was pressed, and passes the message into the computer's main system in a particular way. Specifically, it triggers what is called an interrupt. An interrupt is just what the word sounds like. It's a small signal that taps the main processor on the shoulder and says, in effect, drop what you're doing, something has come up. The processor, when it gets an interrupt, remembers exactly where it was in whatever it had been working on, so that it can come back to it later. Then it jumps to a small piece of code that has been prepared in advance to handle whatever just happened. That piece of code is part of the operating system. It is called, for the obvious reason, an interrupt handler. The interrupt handler for keyboard interrupts is a small piece of code that reads the message the USB controller has prepared and figures out which key was pressed. It then notifies the operating system that a key has been pressed. The operating system, knowing which application is currently in focus, sends the information about the key press to that application. The application, which until this moment had been sitting idle, waiting for something to happen, now receives the news that the A key has been pressed. The application has a piece of code that handles key presses. This code decides what to do with the new letter. If the application is a word processor, it inserts the letter A into the document at the current cursor position. It updates its internal representation of the document. It marks the part of the screen that needs to be redrawn. The application then tells the operating system that it needs to update part of the screen. The operating system handles the actual drawing by sending instructions to another part of the computer called the graphics processor. The graphics processor in modern computers is a separate chip specialized for drawing pictures. It has its own memory, its own way of working, and its own set of instructions, all designed for the particular kind of math that drawing on a screen requires. The main processor sends it requests about what to draw, and the graphics processor figures out exactly which dots on the screen need to be changed to which colors. The graphics processor writes the new colors into a region of its memory that holds, at any given moment, a complete picture of what the screen is supposed to look like. There is one entry in that memory for every dot on the screen, telling the dot what color to be. The contents of that memory are continuously being sent, 60 or more times a second, to the screen itself, either through a cable running between the computer and the screen or through an internal connection if the screen is built into the computer. The screen, on receiving the new information, updates its dots accordingly. The dots are, on a modern flat panel, tiny electronic elements that can produce different colors when they receive different electrical signals. The letter A appears on the screen, in the right place, in the right font, in the right color. From your perspective, you pressed a key and the letter appeared. From the computer's perspective, a small message traveled through a chain of about a dozen different pieces of hardware and software, each one doing a small specific job, in a total time of a few thousandths of a second. This is, more or less, what happens every time you do anything on a computer. The specific details vary. A mouse click goes through a similar but different chain. A network packet arriving from the internet goes through a different chain. A piece of audio coming out of the speakers goes through yet another. But the general pattern is always the same. Some input arrives at some piece of hardware. The hardware notices the input and tells the operating system. The operating system tells the relevant application. The application processes the input and decides what to do. The application tells the operating system what should happen on some output device. The operating system tells the output hardware. The output hardware produces the result. All of this is built, ultimately, on top of the basic operations we talked about at the beginning of tonight's story. The transistors are switching on and off. The logic gates are performing ANDs and ORs and NOTs. The processor is fetching and decoding and executing instructions. The memory is holding bits. The operating system is choreographing the whole thing. A modern computer, when it is running normally, is doing something on the order of 1 trillion of these tiny operations per second. The work it does in any given second is the sum of an enormous number of individually small steps, each of which is one of the basic operations Boole described in 1854. The fact that this all works, and that you can press a key and have a letter appear on the screen without ever noticing the trillions of small operations happening underneath, is one of the more remarkable engineering accomplishments in human history. The fact that the same machine, built out of the same trillions of tiny operations, can also play music, and stream video, and run video games, and find words you type into a search box, and translate languages, and do nearly everything else that computers do that is the consequence of the fact that once you can do logic, you can do everything. Closing. If you have stayed with this story from the beginning, and if you haven't, that's exactly as it was meant to be, you may have noticed something about the way computers were built. They were built in layers. Each layer was built on top of the layer below it. Each layer hid the complexity of the layer below it from the layer above it. The transistors hide the messy physics of electrons in semiconductor crystals. The logic gates hide the transistors. The processor architecture hides the logic gates. The machine instructions hide the processor architecture. The programming languages hide the machine instructions. The operating system hides the differences between hardware. The applications hide the operating system. You, the user, see only the applications, and you only see those when you have to. This stack of layers, each one hiding the layers below it, is what makes computers usable. Nobody, not even the most experienced computer scientist, understands every layer in detail. A person who designs computer chips might know almost nothing about how applications are built. A person who writes applications might know almost nothing about how chips are made. Each person works at their own layer, trusting the layers below them to do what they say they will do, and providing services to the layers above them. The whole system, when it works, is one of the most successful examples of large-scale division of labor in human history. The story of how the layers were built when you walk through it is a story of small specific people in small specific places, each working on the one layer they cared about. A graduate student in a basement at MIT, connecting Boolean algebra to switches. A self-taught mathematician in Cork, writing down the algebra 80 years earlier. 3 men at Bell Labs, frustrated with vacuum tubes, building the first transistor in December of 1947. A new employee at Texas Instruments, alone in the building over a summer holiday, sketching the first integrated circuit. A Hungarian mathematician in a hospital in Aberdeen, Maryland, writing the architecture that nearly every computer would follow. A young engineer at MIT, threading magnetic rings onto a grid of wires. A Navy officer at Eckert Mauchly, deciding that programs should be readable by humans. 2 researchers at Bell Labs, building Unix so that one of them could play his spaceship game. None of these people, at the time they did their work, knew that they were building the world the rest of us would live in. They were each solving a problem in front of them. The cumulative result, after 80 years, is the small object in your hand or on your desk or in your bag, which contains, by some recent count, the computational power that the entire planet had in the 1980s, packed into a piece of silicon the size of a fingernail. What you have when you use a computer is a system that runs on a stack of decisions made by people who are mostly dead now. The transistors in the chip in your phone are descendants of the device Bardeen and Brattain made in December of 1947. The architecture of the chip is a descendant of the design von Neumann sketched in the spring of 1945. The operating system on your phone is a descendant of the system Thomson wrote in the summer of 1969. The applications you use were written in languages that are descendants of the ones Hopper and Backus designed in the 1950s. The whole stack, top to bottom, is built on agreements made decades ago that the makers of the layer above could trust the makers of the layer below. You don't need to remember any of this. You especially don't need to feel that you should have known it before. Most people don't know it. Most people use computers every day without ever asking how they work, and that is fine, because computers are designed to be usable without being understood. The layers are designed to hide their own complexity. The whole system is designed so that you can tap an icon and not have to think about what happens next. But if you have stayed with the story, or if you remember any fragments of it in the morning, you will know, in some small way, more than you did when the night began. You will know that there are no fundamental mysteries here. You will know that the computer is a stack of layers, each one doing a small specific job, and that the layers all the way down are made of switches that can be on or off. You will know that the whole apparatus is just Boolean algebra, performed very fast, on very many bits by very many switches. There is, when you sit with this for a while, a particular kind of strange beauty in it. The machine on your desk, when it is doing its most impressive work, is not doing anything fundamentally different from what George Boole described in 1854. It is, in some sense, the same idea being done very fast and very often, with extraordinarily small switches. The whole modern world of computers, from search engines to video games to artificial intelligence, is the consequence of doing logic faster and faster on more and more bits, year after year, for 80 years. The underlying activity has been the same activity the whole time. The astonishing variety we see is the result of accumulated speed, accumulated density, accumulated layers built on top of each other. The room you are in is quiet now. The lights, if you left them on, can stay on or turn off. The blanket, if you pulled it up, is still where you left it. The phone or the screen you are listening through is, right at this moment, performing the operations we just walked through, several billion times per second, somewhere in its small silicon brain. The fans, if any, are quiet. The processor is, at this exact second, fetching another instruction, decoding it, executing it, moving on to the next. The story we have told tonight is, in a real sense, the story of what your phone is doing right now while you fall asleep. The story will still be here in the morning. Nothing in the rest of the world is asking anything of you right now. Sleep well.